In this lecture, we use spectral sequence to prove the 5 lemma. So let us recall what is the 5 lemma. So in the 5 lemma, you're given a commutative diagram like this. So there are 5 columns. That's why it is called a 5 lemma. Here the rows are exact. So these green arrows are exact. So in general, the 5 lemma has arrows pointing in the opposite direction, but we are using this convention of going towards the left because we want to fit this diagram into the spectral sequence setup. So the 5 lemma says if the rows are exact, that is all these green arrows are exact, and phi2 and phi4 are monomorphisms. So phi2 and phi4 are monomorphisms. So that means the kernel of phi2 is 0 and kernel of phi4 is 0. So this we are going to use later on. And phi5 is an epimorphism. So this phi5, this is an epimorphism. So that means co-kernel of phi5 is 0. Then this phi3 is a monomorphism. So that is, we have to show that kernel of phi3 is 0. So this is what we have to show. So if the rows are exact, phi2 and phi4 are monomorphisms, phi5 is epimorphism, then phi3 is a monomorphism. So we have to prove that phi3 is a monomorphism. That is, we have to show that kernel of phi3 is 0. So we are going to use the homological version of the spectral sequences. So the arrow convention is on page R, we move R left and R minus 1 up. So we are going to fit this diagram on page 1. So we are going to fit it on page 1 first. So you use the row filtration or the horizontal filtration. So you forget about the vertical arrows. And then we get a complex like this. So we are just copying the row down here and copying the bottom row down here, but we want to make this row exact, so you have to put kernel behind it. So kernel of this map, so say this map is f, so you put kernel of f here, which will be injective, and there is obviously a 0 coming in here. So say this is f1, f1, so if this map is f2, then you put kernel of f2 here and 0 coming in here, so this map is automatically injective. Similarly, you can put g1 and g2 here, and again make this top row exact by going like this. So you have co-kernel of g1 right here, and you have co-kernel of g2 right here. So this goes to 0, this goes to 0. So we are on page 1. So this is how the arrows will go like, because on page 1 you go 1 left. So on page 1, this is our convention, r left, r minus 1 up. So 1 minus 1 is 0 up and 1 left, and that's what we have. So now you have 2 rows which are exact. Now if you have exact rows, then you immediately know that the homology of the total complex is going to be 0. So we now know the page infinity is 0. Because of our horizontal filtration, we were able to fit it on page 1, and that's precisely why we reverse the arrows here, because in usual snake lemma the arrows are going like this, and what we are doing is we are taking arrows in this direction. So we could fit this on page 1. We got 2 exact rows after doing some manipulation with f1, f2, g1, g2. They were exact, therefore means the homology of total complex is just 0. So page infinity just completely consists of 0 in every PQ position. So you know page infinity is like a chessboard, and on every chessboard sits a 0 module. So now we use the column filtration or the vertical filtration. So we are just copying our complex from the previous slide. Here you have E1 to E2, D1 to D2. So just your map phi1, phi2, phi3, phi4, phi5, and the kernels here and the co-kernels here. So on page 0, you know the convention is that you go 0 left and minus 1 up. So your convention is r left, r minus 1 up. So you put 0 left, minus 1 up. So that is 1 down. So that is our convention for page 0. So now we are back on page 0, but now we have column filtration or vertical filtration to be precise. So we have vertical filtration. So once we have this, you already know that 0 goes in here and 0 comes out here, 0 goes in here and 0 comes out here, and similarly for everything else. So a general fact is, so if you have a sequence like this and says this is some map f, and someone asks you to compute the homology of this. So what is the homology? So homology here would be kernel of f, and the homology here is co-kernel of f, and that is precisely what we are going to use. So from page 0, when you go to page 1, you take the homologies. So here we are not even writing anything. So say there is some homology here, some homology here. So homology here we write as star 1, homology here we write as star 3. So here you use this formula here. So you have kernel of phi 1, co-kernel of phi 1. Here you have kernel of phi 2 and co-kernel of phi 2. Here you have kernel of phi 3 and co-kernel of phi 3. Corresponding to this, we have this kernel of phi 4, co-kernel of phi 4. Corresponding to this, we have kernel of phi 5, co-kernel of phi 5. Here we are not explicitly mentioning what the homology is. So say there is some homology here which we put as this big star 2. There is some homology here which we put as big star 4. So now we are on page 1. Again our convention is r left, r minus 1 up. So you have 1 left, 1 minus 1, 0 up. So 1 left and 0 up, and the arrows are in this direction. So immediately notice that this is our assumption that phi 2 and phi 4 are monomorphisms, that is kernel of phi 2 is 0 and kernel of phi 4 is 0. So this kernel is 0 and this kernel is 0 and this co-kernel is 0. Now this is important because the arrows are given to us and you start computing the homology for any module M. If you have 0 going in and 0 coming out, you compute its homology, you still get M, because homology is the kernel of this map, and because the image coming in is 0 and the kernel is the entire module M. So if you take homology with respect to this map here, because you have a 0 here and a 0 here, this will just stabilize to kernel of phi 3. So when we go to page 2, we will have this homology sitting here. So let us now draw page 2 up here. So on page 2, corresponding to these two rows, we have these two rows. This is the row above it and row below it, which just have zeros in it. Now, so homology of this row we are writing here. So corresponding to here, you have this homology, which is some losange I have put as 2 here, and corresponding to this you have some here 4. This is just a 0 module, so since homology is a submodule of this is also going to be 0. Corresponding to here, homology we are writing as star 5. This is just 0, so its homology will also be 0. And we mentioned before this kernel of phi 3, the homology here will just be kernel of phi 3 because there are 2 zeros here. So you have kernel of phi 3. This 0 just copies here. Homology at this point you write as this star 1. Homology at this point, because this is also going to 0 here, and you have 0 coming in. So you have a homology here which you write as losange 1. Similarly, you can compute homology here, which is this losange 3. Homology here you write as double star 1. Homology here you write as double star 2. Homology here you write as double star 3. Homology here you write as double star 4. Now notice that we have to prove that kernel of phi 3 is 0. So since we are sitting on page 2 and our convention of arrows is r left, r minus 1 up, so you have 2 left and 1 up. So notice that from this 0 you go 2 left, 1 up, you're landing in kernel of phi 3, and obviously above and below these two rows there is just zeros, because this page is obtained by taking homologies on this page, on page 1, and these are the only two rows which have non-zero entries. So now notice that this kernel of phi 3 has stabilized. If you take its homology on page 3, you will still get kernel of phi 3, because this is a module of this form 0 m 0, and if you take the homology of such a chain you just get m. So on page 3 this is stabilized, so this is on page 3. Similarly on page 4 it will again be kernel of phi 3, because zeros will be coming in and going out of it, and so on. So the arrows are getting bigger on further pages. So from page 3 all the way to page infinity, this entry just remains kernel of phi 3. But we already know on page infinity you are putting zeros everywhere, so we are going to put zeros everywhere. So it has to be the case, since it is stabilizing on page 3, that this kernel of phi 3 is equal to the 0 page, 0 entry on the infinity page, because infinity page just consists of 0 entries. So again what we had to prove, that kernel of phi 3 is 0, and we are saying kernel of phi 3 is 0 because everything stabilizes after this page. Because if you take the homology here of such a chain complex, it is just m. You take homology here, you're going from 0 to kernel of phi 3 to 0. It will always be kernel of phi 3. So it kind of stabilizes here, and since it stabilizes, it has to take value kernel of phi 3 on page infinity, but on page infinity you just have 0. So we have been able to prove that kernel of phi3 is 0, which we set out to prove, and therefore phi3 is a monomorphism. Now you can see that this entire game was rigged, in the sense that we needed two zeros here first. So we needed this monomorphism right here and here, so that we can pick this kernel of phi3 and put it right here. And we already knew on page 2 the arrow going out of kernel of phi3 will be 0 anyway, because this 0 is computed from homology of some row above here, which anyway consists of 0. But for this kernel of phi3 to be 0, we had to have 0 coming into it, so that this kernel of phi3 is stabilized. And that is precisely why this co-kernel of phi5 was taken as 0, because it is this 0 which is sitting here. So there are other versions of 5 lemma also, but what you need to do is you just have to draw this diagram. Just draw this page 1, and then see which places you have to put zeros to make sure what condition you have. So you can again put a condition on there's another 5 lemma version which puts a condition on co-kernel of phi3, that is phi3 is an epimorphism. So for this to happen, you can immediately say what you have to do. You have to make it stable here, then you have to put this as 0, this is 0, so this thing gets copied right here, and then you know that 0 is coming into it, but 0 has to be coming out of it, so this has to be 0. So then you have to say that this phi1 is a monomorphism or something like that. So this is an easy way to see a proof of 5 lemma.